that day, and you just don't really have to ask anymore. It's just pretty much half the classes in there coming back and forth all day. So I'm kind of getting used to that already. So you should have, I think it's this two-way ANOVA lecture notes. This is the stuff that I had did that last class. So you're going to need that file, right, to do this. But otherwise, I'm not going to do SAS today. We got a bunch of people that are actually out in the field. So they told me they were out today. But today we're going to start the first lecture in a series of data management, and the later ones are going to get into SAS. But for right now, this is just basic overall concepts of managing your digital data and storing your digital data and all about that. And I know that pretty much everybody in here is taking maybe 2 or 3 other computer classes at the same time, right? And computing isn't exactly your strong suit. And so I started putting some of this together with Paul, and then he said, I don't even know some of these things either. And they're some of the reasons why we do things even in our office. He just like, oh, I didn't put 2 and 2 together, that's why we do that. So anyway, so here's the thing, and so I found this on The Onion the other day, which was really funny. The area dad was concerned that he's running out of family photos digitized. That was yesterday's headline. And so it kind of goes along with that. So this is mainly intended for science people, for everyone in this room that's taking data. But you could apply these same sorts of principles to your own personal data life as well. So it's kind of good information to know. All right, so the punchline is that data management is basically a BFD. And I don't know if Paul actually said what BFD stands for. I guess figure that out. For ecology, because we can't go back in time to retake observations. And as weird as it may seem, because I think almost everyone in here is doing some sort of field work, right? It's like everybody out in the field taking some sort of data. You're not. Are you going to at some point? I know you're going to at some point, so that you're going to be doing that. And are you taking data? You're taking data. You're not taking any data right now.
No, I'm switching to professional track, but I was going to be. So.
You were going to be.
So I have it on.
And it's really.
My butts in the laughter for 2 years.
Yeah, I know you will, Megan, but you're not there yet. But the thing is, you go and you do a field study when you're a graduate student. And so I did a field study when I was a graduate student. And at the time, I'm like, my BS little graduate student study is not gonna, so what? I went out in the Bay and did some stuff. Well, when you think about it, that was the only time someone went out to the field to collect that type of measurement at that specific place at that specific time. And when you step back, it was, well, I'm the only one in the Bay doing this work right now. So I was the only one in Corpus Christi Bay that did that record. So when you think of the responsibility you have to future science, it's actually the life of your study will extend much further than your own personal career. And even that, like, look at the data that Paul does in class. Most of the stuff was taken in the 80s. And I was at least born then, but I think some people in class probably weren't born at the time he took the study. But, I'm just saying that these things will go on. And at the end of this, we're going to get into some case studies about that. But basically, these things will never occur again. Unlike a laboratory setup, the whole point of a laboratory experiment is this should be repeatable. You should be able to repeat that. We cannot repeat an ecological study, ever, in that exact form. Again, that's the only time it will ever occur. So we have to save that not only for us, but everyone else. So the outline of this is I'm going to go through physical formats of how a computer stores information. How it physically stores it, how it logically stores information, what all these terms mean that you've heard thrown around in class. I know you've heard a few times, probably in your other class, about what's a float, an int, these things, because you don't have a computer background, so you weren't ingrained in that. But that way it gives you this information. This really should have been like one of the first lectures we did in the class, but we just had time this time for me to do it. I'm going to get into metadata that I know you've heard about before, but we're going to get into some real specific examples of why we need metadata and what to put in metadata. We're going to talk about data loss and prevention. There are 3 main ways you lose data, and we're going to go through some case studies. Some of them are famous examples, some of them are examples of people that work down the hall from us, of different things. So here's a case study. I don't know if you've heard this. This was in the news maybe a few months ago. This is the Veterans Affairs Records Office for people getting their veteran checks, and it was a famous thing in the news a few months ago about that. I don't know if anybody remembers about that, but they had their too many records in one room, and it was actually breaking the floor that had too much stuff in it. And then if we have time at the end of the class, then we're going to take a metadata example and try to chart it out. So someone's field experiment that they're doing, I'd like to pick on someone else, so maybe yours, we'll see when we get to the end. We have time. All right, so bits. You all know this. This is something everybody knows, right? A bit is an on or an off. It's the most basic level of information that is stored. Everything physically is eventually stored as ones or zeros. No matter what logical representation it is, if you think it's in hexadecimal or some weird thing, it's in ones or zeros. That's it. Everything else on top of that is some way for us to read it. Okay? And so here's a switch, here's a gate that's 1 nanometer big, and basically it's just, is there an electrical impulse, yes or no? There is no in-between at all, at least not yet until they have this thing called a quantum computer that could have a maybe state. And that could be way, way, way down the road, way in our future. Okay, so then let's move up, a little bit more complexity. Now we get to this thing called hexadecimal. So if anybody saw the Martian movie, and you remember in the Martian movie when he's like, he's trying to talk to NASA on the Mars rover, and he's like sticking up the signs, yes or no, and the guy was like, you know, got his nerd hat on. He's like, it's going to take 16 years for him to chart out by basically binary, yes or no, that he needs something. So to save space, we're gonna use ASCII or use hex, right? And so to save space and time, we use hexadecimal as a way to visualize binary data. The computer doesn't store it in hexadecimal. It's just for us to read it and do math on it. And whenever we work at a different number system, it's commonly referred that you see the number system, and then at the bottom in the subscript you have what base system are you using it. So you learned to count when you were in a kindergarten, and we learned in the base 10 system. So everything in your personal life is ingrained base 10. The computer is base 2. There's only 2 things it could be, 1 or 0. Base 16 is hex. So after you get past 9, then you have A, B, C, D, E, and F. And then you roll back over. So if you have 10 in hex, if you see 10, that's actually 17 for everybody else, right? So that's why it's really important that whenever you work with something in the computers, you see some sort of either base 16 or you'll see an X. That's when you know that's going to be in hex. So, but just to reiterate, the computers don't think in hexadecimal. They think in binary. That's just for us to read it, to us to pack, because otherwise you're stringing so many zeros and ones out, you can't make any sense of that. All right, so now we have bytes. So bytes are the smallest collection of bits, and typically it's 8 bits or 2 hex digits, and a byte can hold 256 unique combinations. All right. Now the problem is that when someone says that's a byte, like this file is so many megabytes, the byte is becoming less and less uniform as time goes on. But as we'll get in the next couple of slides, as our architecture changes, the size of those bytes change. And that's why when you see network speeds, they always refer to it as bits per second instead of bytes per second. That's why they do that. Because other computers, depending on your architecture, the size of my byte on my computer could be different than the size of your byte on your computer. And so when you're saying I can move 2 gigabytes a second, they're saying, well, 2 gigabytes, whose gigabytes are you talking about? So that's why they refer to it as just bits per second. So maybe that made some people clear on that. I mean, you've heard that, right? The bits per second versus megabytes per second. And so when you're looking at buying internet, there's a difference in that. So now, let's string some bytes together. When we group bytes together, they're called a word. And typically, again, it's 2 bytes, so it's 8 bits together, and it's 4 hex digits. So right here I've got in binary or in hexadecimal. So a 16-bit word is 4 hex digits, and that's 65,000 different unique combinations. Now the reason why I even mention what a word is, because I probably guarantee no one's ever heard of, you've heard of a byte, probably haven't heard of a word. The word is important because when a computer is 32-bit or 64-bit, that's how big the word is. And that's the size. So it's essentially you're talking about the word size of the computer. So it's either going to be that 32-bit or 64-bit. And so that's why I'm saying that the size of the bytes can change. So depending on if you're a 32-bit or 64-bit, that moves. All right? And here's the other really confusing thing. This Paul didn't know this either. Is this thing called Indianness. Back in the day, way back in the day, when they were forming how they were going to physically store information on a computer, the different computer manufacturers did it differently. And it's sort of like reading left to right versus right to left. You know, like I think in Japan they read right to left, right? They read the opposite way. Different architectures actually store the values of words opposite. And this problem was about to die away and just be dead because the Intel architecture is called the Little Endian, and that was taking over. And pretty much everything was moving to Intel architecture. The only thing that did Big Endian is like IBM mainframes. This is even up until maybe 10 years ago. Big mainframes were in Big Endian. So if you move data back and forth, you have to run it through an algorithm to actually flip-flop everything so that you can actually open your file up. But now, Big Endian's coming back because they're using it on mobile devices. So Xboxes, phones, tablets, older Macs were Big Endian. So this could actually be important if you're taking data, actual binary data, on a tablet device or a phone. And then you move that file off and try to open it on your Windows computer, it won't open up without the byte-wise conversion. Okay? So what is the difference between 32 and 64-bit? Everybody's heard this, right? And I remember we had this whole problem about, well, we have to have 32-bit this software, 64-bit this. Essentially, it's the size of the address of memory, that word size. And it's called the pointer. And it's what is used to retrieve data stored in memory. So the bigger your address scheme, the more numbers you have, and therefore the bigger memory you had. So a 32-bit computer could only have 4 gigabytes of memory. That was the wall we hit up recently. And that's why everybody moved to 64-bit, because you needed more than 4 gigs of memory. So we needed more addresses. So the problem, though, becomes that if you've got more addresses, now we have to use the whole thing to make a call. You can't just like chop it down and say, I just want to call someone next door. I don't need to use all the numbers. And it's the same thing that we have for area codes and phone numbers. So way back in the day, like my parents' age, when they were kids, they only needed 4 numbers to call someone down the road. And of course, really old, they just picked up the phone and said, I want to call Susie Q down the road, and then the operator lady sticks it in, and that's it. You didn't even have a number, you know, way when the phones were first out. Then it came to just 4 numbers. And everybody was really easy to memorize those phone numbers. Then they had to get this whole 3 more prefix and then the 4. And we did that for a long time. And then now the area codes came out. And I've been in Corpus long enough. We were used to be in the 512 area code. And then it got too big. So then they gave us the 361 code. And everyone got pissed because you had changed all your business cards to 361. And now, if you don't have the area code, you just can't call someone. You have to give them the area code. Because almost everybody has, from this room, most people in this room probably don't even have a 361 code anyway. So on these forms that says my 5-year-old knows how to call home, I'm like, well, what do you like? You mean like the 10-digit code? Because he needs to remember that whole thing. So the problem is that now we've gotten to this issue where that address is getting longer and longer and longer. Maybe it's someday we might actually refer to phone numbers as and hex, because like divided nearly in half, right? So that's the difference of that. Now, why is it important? Because that bit size, the 32-bit, 64-bit, changes the word size and changes your byte size. Therefore, when you create a binary data in a 64-bit computer, it's going to require twice as much space as a 32-bit computer, or it can, if you're creating 32-bit integers versus a 64-bit integer, which we'll talk about. Now, most programs are pretty good about being backwards compatible about this. Like, say, if I did something in Microsoft Word 64-bit and I emailed it to someone in class, you're going to be able to open that up because it's backwards. They've written in for it to be backwards compatible. However, if I create a specialized program, either through a class that I did or I have some specialized lab equipment, and it's running on a 32-bit computer and it's doing 32-bit integers, and I'm assuming then I open it up on a 64-bit, it's not going to work, right? So that's what you have to also keep into mind yourself about. Maybe just one more thing about 32 or 64, and people sometimes ask me, well, are we ever going to get to 128-bit computers? The thing now is that with the 32-bit computer, you had 32 to the second spaces to address something. So that's 4 gigabytes of memory you could have. With the 64-bit, it's, oh, actually, this is totally wrong. It's 2 to the 32. You have 2 to the 32 spaces. With 64-bit, you have 2 to the 64. And that's in some Wonga, I don't even know what it's not even EXA, or it's way out there. We're probably not going to need that. We're going to that situation we had where we needed to get more than 4 gigs of memory probably won't be the problem. However, we might move to 128-bit computers just because the speed of processors is now fixed and constant because we can't make them any faster. For one, we have a speed of light problem. We can't make the speed of light go any faster between transistors. And if we pump any more energy in them, they're going to be hotter than the surface of the sun. So that's why computer processors now are about 3 or 4 gigahertz a pop, and that's it. That's the max. So, but if you have a 32-bit computer and you're able to do an operation at 3 gigahertz on a 32-bit number every 3 gigahertz, and then you move to 64-bit, now we have a 64-bit operation we can do. So remember at the time when we moved to 32 to 64-bit, and I was in an HPC lab at the time, we were doing high-performance computing, the computers that we bought from Dell had the same gigahertz. Well, the next one was 64-bit. That was twice as fast as the last computer because we were doing a 64-bit operation each clock cycle. So in other words, they might move to 128 or 256-bit because you can do those operations in one clock cycle instead of doing 4 of them in a row, right? So that could be why at some point we move. So as kind of rounding out the last of the physically changing your data is encryption versus compression. So as weird as it may sound, binary data often includes lots of unused space. And that's really true of ASCII files when we get talking about ASCII files. Because you have to have you have to have at least 256 bits just for one letter, right? And really there's only 26 letters. So a lot of times when you look at a file, there's repeats and repeats and repeats. Compression, what it does is it just shrinks the size of the files, right? However, encryption does the opposite. Encryption bloats the size of your files, right? And either method will result in a new binary file that cannot be opened until you pass it through an algorithm of some sort, whatever you put it through before. So, like for an example, the zip thing has been around a long, long time. That's been around since the 80s. And it's really a collection of several algorithms. And inside the file, it says what algorithm I'm using in the metadata of the file. So when you open it with Windows or Unix or Linux, it tells it, hey, I use this algorithm. It's to this bit size, run this, and then it uncompresses the file. Another example is this thing called an MD5 hash. And you might have heard of that before. And we'll talk about that, even a little example of that later as well. MD5, what it does is an algorithm. You run it through a whole file, and it produces a key, a 128-bit key of the file. And it's commonly used to just verify file integrity. So if I have this big, big file, I run this program and I get a small key. Then I can hand that small key to, say, Megan and say, here's the key to this file. Now you're going to download this 5 gig file, and to make sure it actually got there okay and didn't get corrupted somewhere between, run this hash, you should get the same key. So that's why you often see that key displayed when you go download big files sometime, or especially with data sets and anything that's really integral data that's priority that you need to know it was downloaded correctly. Okay? So now let's get into logical formats. We're done with the physical. That's physically how things was stored. Now we can talk about logical stuff. The logical, in programming, we define these logical formats to expect a certain type of value. And again, between your 32 or 64-bit, the actual storage size you use for these will be different, but the program will be the same. So I could write a program and say, I want to use this integer. I run it on my computer. The actual physical size that that number took up could be different in my computer than in your computer. Physically stored, different size. Could be bigger or smaller. Also within, if I ran in Python versus running in C, and say an integer. Like the other day I did a size of, and apparently in Python it takes 16 bytes to store an integer, which is huge compared to C, which would be 8 bytes. So an integer, and whenever we refer to that in all your programming classes, an integer should be a number without a decimal point. And typically it's small. Okay? A Boolean is a true or false. It's basically just one bit. Is it on or is it off? And you use those for logic sometimes. So if you ever have something you need to do like a true or false, is this true or false? And save that somewhere. That's just a Boolean. A floating point number is numbers with more storage, but the standard is 7 digits of precision. And one thing that people that are not really into computing can forget is that it's only 7 digits of precision. So if you're doing something that requires a lot of precision, you need to store something other than a float, especially if you're doing operations on it. Because at some point, only 7 digits is not enough. And that's why you get to this thing called a double. If you've ever heard of that before, stored as a double. So if you're taking a Python class or anything of that sort, a lot of these modern languages will automatically do these things for you. Olden days they didn't. You had to just specify. SAS is kind of in between. You know, we can set things as a string, and then we do that format statement, and we say, I want exactly this many digits in SAS. So we have a lot more control in SAS over specific digits than you do in, say, other languages. A character is just a single letter. That's it. That's all that can be stored in a character, just one ASCII character. And a string is just an array of characters. And usually you'll see, like if you look at a programming language, you'll see a character with one quote. That's going to say whatever is in here is one ASCII character, and then double quotes for a string, multiple ASCII characters. So that's kind of a common, if you see that in other classes or other people doing that, that's a common way of representing that. Okay. So the ASCII standard. This was invented as a way to visualize binary data way, way, way back in the day, in the 60s. And when they first came out with ASCII, it was extremely small. It wasn't even a byte. You could just use a hex character. Then they finally got to be a byte, and so we need more. And the problem we have is that we keep having to increase the storage capacity of ASCII. And now we're up to Unicode, and so whenever you do a Unicode in SAS, you're using 32 bits to represent whatever that item is. And part of the problem is that ASCII was only invented for the Western countries, so we don't have any of the letters for anybody else in the ASCII standard, right? And so if you're in one of these other countries, you end up having to use your own standard because otherwise ASCII would be so huge you would need this giant amount of space just to represent one number. But it does include numbers, letters, special characters, white space, and for us people that deal in the Western language, it's great. It can work for us, right? But it has these extra space usage. So one item that I like to talk about, and I know everyone's had this problem, and I'll show you an example on my computer in a second, is this thing called carriage return and line feed in ASCII. A carriage return and a line feed are both white space characters. You can't see them. In fact, they're not even. It's not even something you can select when you're looking at something in Word or in a text document. But back in the 60s, most computers weren't even hooked up to a monitor. Most computers outputted to a printer. And in ASCII, there is a ton of these control characters that are built into ASCII. I mean, there's at least like 20 or 30 of them, these control characters that control all sorts of things. And one is carriage return and line feed. So what carriage return did is it took the typewriter, it sent a message to the typewriter. The typewriter takes the carriage, the thing that types the numbers, and returns it back to the left. The line feed said, push this and make one more line of paper go up. And when you were working on the computer and you were typing your program, you had to put carriage return and line feed. Those were commands. So when the typewriter gets the commands, it's just going to print it out. You know, it's printing out the ASCII. When it gets to a carriage return, it says, oh, move that carriage over. It gets to a line feed, move the line up. Two completely different operations. You had to have those two things. Otherwise, if you didn't put it in it, then it would just keep printing over here, right? And you just end up with a big mass of black, which I'm pretty sure a lot of computer science students back in the 60s probably did that at some point. Had like a big line of black at the end because they didn't move the thing over. All right, so the deal that's important to us is that in a lot of wisdom back in the day, and this is a logical thing, that when you worked on a Mac or a Unix, they assumed, okay, we only need carriage return. We figured that out. Like, we're working on a screen, okay? If you just give me the carriage return, that's a new line. That's it. That's all I need. However, Bill Gates, when he wrote DOS, said, no, 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 you still need to have both. You still need to have both. Just to be out of the way it is. So now, if you wrote a text file in a Mac in 1982, and I handed it to somebody else in class and they opened it up, everything would be on one line, right? And so we'll see that, because this happens today. This happens all the time. And so I don't know if anybody else has ever seen this. I'm sure you have. You just probably didn't know why this was the way it was. So I've got a USGS data file that I downloaded from the USGS site in ASCII. And it's a text file. It's this here. I don't know what site. It's that site. I don't know what it is. Somewhere. I think it's one of the Trinity River or something like that. So if I just click and open it up in Notepad in my Windows computer, I get this funkiness. right? So has everybody seen this, right? Everybody's done this, they open up a text file, and then why the hell save it in WordPad? And since it's Microsoft, and Microsoft is so into using the carriage return and the line feed, it's going to shove those back in there. So if I just save on top, I don't even do anything to it. Now I open it in Notepad. Look at that. Because now I've changed the file. WordPad changed the file and stuck the carriage returns in to every line. So if you ever have that problem where you open a file and you get this ASCII file and it blows stuff way to the end because you wrote it in one of these programming languages you use in other classes, because if you don't actually, like when you're writing something in Python or what, and I do this all the time, and I print something, and then I only do that, I'm only getting the line pull up. You have to do, well, actually it's should be doing it like this: carriage return, line feed. Then you get both of those. Then you can open it up in Windows without having to do that two-step conversion process. Okay. So here's my next little example. Can you open a binary file as ASCII? Has anybody ever done this before? Just to try it and see what happens? This is actually pretty fun. So I'm going to take an example file. I took this picture during my worthless graduate field study. And I took that picture, and I'm going to trick Windows into thinking it's a text file. So I'm going to take the picture, and I'm going to rename the last digits .txt. And I'm going to open it up. What do you think that we're going to see when we do that? I mean, so do you think that we're going to see ones and zeros? Probably not, right? You think we're going to see hex characters? No, because the notepad, it's assuming it's ASCII, right? So what it's going to do is it's going to read those actual ones and zeros and put them in 256 byte chunks. And each of those chunks, it's going to look up through the ASCII table and say, it's that character. Okay? So we're going to get some gobbledygook. So what I'm going to do is, actually, I'm going to make a copy of it. Because I don't want to open it in something and save over top of it. Okay, so the copy, I'm going to say text. And say it might be unusable, okay. All right, so here's the picture of my bird. I think I don't know if there's two legs there, or he was missing a leg, or a leg is up. I don't know how they do that. But that was at Cole Park Pier. And that was in 2012 when I did my study. All right, so let's open this up. And let's see what we find. This is pretty. Okay, so we see some gobbledygook, right? You ever had a file and you have stuff like this, right? That's because whatever you were doing, that's a binary file. And whatever you were looking at it was assuming it's ASCII. So regardless of how big those floats were or anything, it didn't know any of that. It's just taking those chunks and looking up in the ASCII table, and that's what you get in the ASCII table, and since the ASCII table is so big, and the majority of things are special characters now, right? That's why we keep getting it bigger and bigger to get these special characters. That's why you see nothing but special characters. However, sometimes you see a couple gems. And so what I'm going to do is I'm going to open it up in WordPad now. Okay. Since it word wrap for me, I can read some stuff in there. Why can I read some stuff in there?
Picture has metadata.
Picture had metadata in it. That was actually ASCII text. So, looks like I took it with a Sony A57 in 2013, right? So the FBI loves that kind of stuff, right? Because there's stuff in there. But as you go through these files, and so in my little presentation I have it in here. So we were able to read strings in the file, and we're actually able to read some of the metadata. There's metadata in there that's binary, but we're actually able to read the ASCII stuff in your file. So when you make a program, like say if I made, SAS is text, like the .sas is actually text. If you translate it to just .text, you get text. If you're working in Java or anything else, or Python, any of those languages in these other classes, and you put some ASCII text in your program, and you have, this is like the labels and things, you change the name of your program to .txt, you'll see that somewhere in your file, right? Because that's actually stored in there. So this gets us to what makes up a file. A file has two parts, always, no matter what. It has some sort of header, which is metadata, and it has the body, which is just the binary data, right? And the metadata, you've had to have heard this in other classes, right? People talking about metadata. It's data about data. So in the file I had, you have time, date, and if I had a GPS on the camera, it'd actually say the location of it. So whenever you take a picture with your cell phone, you get a timestamp, a date, location, what type of camera, you get what lens you used, you have other things in there, what size of the data to expect. So in a picture it'll say this is exactly this by this, so it knows where the rows and columns go. So you have a resolution size. You also have some sort of encryption method. Is it a JPEG? Is it this? Which did it use? And if you took that picture and put it in Photoshop, it'll actually put in that, well, the real camera was taken by this, but it's also now the header information for Photoshop gets stuck on top of it, so it was actually edited here. So if you look up any random picture on the internet and do this trick, you'll see a lot of information about that picture. And so it's kind of fun to even look at your own thing. Oop, I did that. So the thing with metadata is just, really there is just never enough. And when we get to data loss, you'll understand why. There's just never enough. And it is as important as the data you're taking to take the metadata. So some example is, for one, variables. So what is the units? It's, a lot of times here's just a number. So when I get data out of an instrument, sometimes it's just a number. They didn't even say what units it's in. Who are the authors? What's the date times? What's the experimental design? What are the coordinates? Where exactly was this? Another thing, I shouldn't have lost number 2. That's for later. External links though. Keywords. Things that you can find in the file. Things that are indexable. So when you have a file that's indexable by Windows, there's actually a keyword section, and that's what gets searched when you do a search. Because it's not, in most cases it doesn't look through the whole file, it's just looking through the header information and your keywords. But also URLs, DOI numbers like for publications, all those things are external references so that you can find the file later. And then also you've got file-specific stuff. This is something that Paul doesn't have any of that in the metadata that he gave y'all. And this is one thing I've actually been adding into some of our metadata, is data about the file itself, just about the format. How many, how many records are in this file should we expect, right? That's good to know, because what if some got pulled off the side, or I need to know when I read this file in that I should be expecting 1,000 records. So if I got 900, I knew that was the end, right? Also, how many rows and columns, or what's the DPI of the picture, things like that, right? That's information about the file itself. So this gets to the really cool stuff. So how is digital data lost? Now that we've gotten this idea of what is digital data, the ones and zeros, things that we can view on it, now how is it lost? And I've looked, the last few days, I've looked through a lot of different cases, and it all boils down to just 3 ways you lose files. The first one is you either is destroyed or deleted somehow. Either you accidentally deleted it, or the file itself is corrupted, it's destroyed. It's gone. That's number 1. Number 2, the file is lost. I cannot find the file. And that's an example of, gee, honey, do you have the phone record from 2005. I know I scanned it. Where is it? I don't know. Done that before. What's the receipt for what you got at Best Buy the other day? I know you scanned it. I don't know. Can't find it. This happens a lot, actually. More than you think it does. It probably has happened to you before. Number 3, the file cannot be accessed. So that one is, I know I have it, I can't open it up. Either it's in some logical format that I don't have anymore, or it's in some physical format I cannot access anymore because I don't have it. A good example is, I had to throw away my VHSs because I don't have a VHS player anymore. I can't play it. It's gone. The other good example, yeah, actually I took a video of my wedding. It's in one of those 8x8 things. I don't have the camera anymore. So it's sitting in a box. I can't open it up. Right? So that's an example of that, as number 3. So everything is either 1, 2, or 3. And actually, I'll only write it down because when we go through the case studies, you'll lose data from either one of those, or all 3. So L1, destroyed. So data is destroyed. L2 is lost. Can't find it. L3 cannot open. We know where it is. We know it's in that hard drive. We can't open it up. Okay. So data backups. Everybody's heard this one, right? Backing up your data. Important. That's important to do. Backing up. Backing up only prevents L1. That's the problem. So there's really 3 types of backups. The first one is a full backup. That's when you just copy everything, right? So we've all done that. We've all done this stuff. The other one is an incremental backup, and that's only the things that have changed from last time. You get to that point because you realize the full backup is too big. So we can't hold the full backup, so we need to just do the stuff that has changed. All right? The problem is when you start to restore that one, it gets to be a real pain. Real easy to do a backup, easy to do that one, but eventually you can't do it. I can't do it. I can't back up everything anymore. I got too much stuff. Even when they say space is cheap, I still have too much stuff. I can't fully back up everything. The other item is version control. Do you require versions? That starts to incrementally increase how much storage space you need to have if you have to keep versions of things. Now, the thing is, when you're working with manuscripts, I'm typing a document, I want a version, right? That would be really nice. But I don't really want versions when I look at experimental data, because when it's golden and it's been blessed and this is my data, I don't want to accidentally open an old copy that has wrong stuff in it, right? So for those, I don't want versions. So it's really a pick and choose on that. So it gets us to this thing, this is a famous rule. It's called the backup rule of 3-2-1. The only way I can remember it is because of the Star Wars Sith Rule 2. So any Star Wars people in here, there's this thing called the Sith Rule 2. There's always 2 bad guys. There's always like the master and the whatever. And so if you find one, there's always another one. And you can't have more than 2 because then they kill each other. So there's only 2. So really, I kind of remember the backup rule because of that. Because really, most people break the 2 part in the rule of 3-2-1. There's a rule of 3-2-1, and this is from these national people that do data. And they said you need 3 copies. 2 of them in different formats, and 1 of them is an offsite. Okay? And we'll go through examples of that. So especially this 2 formats. So example is, I have printed data sheets of my field work. I have a digital copy of that printed sheet, and I have that saved somewhere offsite, at least a digital copy offsite. So that I have a 3-2-1 on that. It's a different format. So another example, the book for this class. Great example. The book for this class is in WordPerfect when Paul typed it up. I've seen him open it up. He has this ancient WordPerfect program running on his computer to open it up because I needed a table out of it. So he's got it in PDF. That's the one you got, right, is the PDF. The real actual document is in this WordPerfect. It only looks good there. You try to open that up in Word, and the text is there, but it's all messed up, and the tables are messed up. So he has to open it up in WordPerfect to get the stuff out. Okay? So there, he's got it in WordPerfect, a PDF, and offsite because it's loaded online. Right? So that's a 3-2-1 example. So when we get to this idea of bit rot, I know I talked about that the other day to somebody, and bit rot is this new term that has come out recently. And bit rot is really a combination of two factors. One of them is the inability to open digital data because of old physical and logical formats. That was that loss number 3. Okay, either some old format I can't open up anymore, either physical or logical. And second one is data degradation due to the physical format itself rotting, dying. That's number 1. So an example of this, have you ever opened a picture up and it looked like that? Anybody ever opened the picture up and it gets good and then it's like it's all funked down the bottom? It ever happened to you? You had bit rot. That photo bit rot on your hard drive or your CD or whatever it is. This has happened to some of my really old photos. So it's essentially the same thing as like this is a book that has rotted. It's what I call bit rot. It is rotting on whatever item it is. So this side, you can't open it up because I don't have a 3.5 floppy disk drive anymore. I just threw them away. I couldn't open it, I just threw it away. This is called the punch card. Back in the 60s, this is how you saved information. These are the actual bytes, and they punch a hole through, and you run it through this machine, and it prints out the actual bytes. And I remember my uncle said, and when he was in grad school, he wrote this really cool science fiction game, and he wanted to save it for all time, so he printed it all. It was really expensive to do. He printed the whole thing out on punch cards, and it's in this box, and it's in the attic. Can't open it up. Now, for this one, though there is an online thing now, you can take a digital picture of it, and they try to take a digital picture and try to put where the pegs are. But then, of course, it's a Fortran program, and that won't run on, you know, you had to get an emulator. I mean, so you start getting, then you get to the logical problem, right? So, time to bit rot. Anything past 5 years is hard drive, your hard drive mechanically spinning should not spin further than 5 years. This is a 6-year-old laptop with the original hard drive in it. I do a thing every day on it to make sure it still goes because it is past lifespan. 5 years hard drive lifespan. Don't expect the hard drive to spin any past that. Magnetic storage, anything. Magnetic storage past 5 years is suspect. Because we live on planet Earth, and planet Earth has a magnetic pole. And so if you have a floppy disk sitting there, or a VHS tape that has magnetic pieces in it, they will start to want to move toward north, right? So past 5 years, anything magnetic is suspect. However, we still have the machines to be able to put them in. You know, we're typically still using that. I'm still using this. It's okay. I can plug it in. The logical format is still intact. It's a file that we still use, no problem. 10 years. Now I read this thing, remember when we were kids and they came out with CDs? Yeah, I'm old. I'm not that old, but I remember telling my dad, I said, and I was like 15 or so, I said, I want a CD player. And he was like, why? Well, because Dad, CDs will last forever. You know, that was like my sales pitch to my dad to buy a CD player at the time. You know, they're supposed to last 100 years, so that's the last music I have to buy. Of course, I only had like 5 cassettes at the time anyway, so it's kind of a silly argument. But anyway, at the time, they said these will last forever. Of course, there's scratches and all that, right? You went with that. But you ever had a CD where like the metal has peeled off the top? Or leave the thing in the car. That'll destroy it in like a month, right? And I have some old movies. I have it in this nice case, like each thing is protected. I pull the movie out and the movie doesn't work because the plastic has come off. So CD lifespan, 10 years. 10 years. Don't expect it to survive after that. It's iffy after that. Okay? Logical format is old, but usually you can still open it up. I can still open stuff up from 10 years ago, no problem. You know, Microsoft Office and what. And typically, I mean, the hardware is starting to get old, but we still have CD drives. Some people do. We're getting to the point now where they don't really sell them in computers anymore. Or they don't have like it's usually an option both. Now I've been noticing they're just selling Blu-rays, and they're not even, they're just skipping the CD laser because it's a separate laser. So we're getting to the point now where you can't even open a CD-ROM. 20 years. The media is completely past lifespan. The format is no longer used. The logical format is no longer used. So you've got a multiple tiered problem. Even if we can still open the logical file up. A great example of this, I've got some ancient old computers with those big hard drives. How do you open that up? With what? You know, what are you gonna, you have to have that computer working to open that up. You can't take that big giant hard drive and what do you do with it? I mean, the connector's like this big old thing. I can't hook it up to here, right? So you've got to have the physical thing working, and then logical format, what are you going to use to open it up? Old WordPerfect from DOS. You almost have to go to like a museum to open from the one computer working from the 80s to get that data off, right? So then you got the issues. So fighting bit rot. How do we fight bit rot? Number one is you have to transfer things to new media all the time. The problem with this is that if we die, who's going to do that for us, right? So we have to keep up to date. You have to keep moving your stuff up to date. Anything that's important to you, you have to keep moving to new media. That helps you with the L1 problem. The next one is use non-proprietary binary formats. That fights the L3 problem, right? So that's the cannot open. Well, I guess the number one actually does 1 and 3, right? That would do 1 and 3. If you put it to new media, then you'd have the new thing. So that should change that. So the other one is keep hard copies if feasible. I know that sounds very counterintuitive coming from a computer person to keep hard copies, but that's another format. In the rule 321, that's rule number 2, right? You have another format. And the last one, and the absolute most important when you're talking about us, is publish your data with your manuscript. So it's there. It's always there. That one helps everything. So then you push that burden onto the people that do that stuff. And they're people that are devoting their lives to trying to keep the scientific knowledge intact. You let them handle that. Okay? So here we get case studies and data loss. So we're going to go through a couple case studies, some things from in-house, some things external, and they all have this L1, 2, 3, and what you could do to minimize L1, L2, L3. Because I'm going to tell you right now, I don't have a perfect 3, 2, 1 backup solution for my stuff. I have lost data both with this, and this, and the more you think about it, the more you start realizing exactly how much data you have lost over time. So as you're sitting here, you're going to be thinking in your head, yeah, I've lost that. Yeah, I've done that. And it's surprising to you. Like it was surprising to me to think, gee, that I've really suffered a lot of bit rot, but I have. So this is an example. I didn't do this case study, but this is one, is a library that the books are rotting away because they don't have enough funds to turn on the dehumidifiers. Right? So that's data loss. So case study. This is one that we have all done. This is a case study on us in the room. Backups of backups of backups. Everybody's got this problem. So in other words, I lost data from L1 before when I was young, and like my computer died and I lost everything. Remember the first time that ever happened to you, right? Mm-hmm. And the first thing you did was, I'm going to back up everything all the freaking time. So then what happened is that now we have created L2 for ourselves by doing a backup program where we don't have enough metadata to go with this. Because now we have this problem where we have backups of backups of backups. What's the real file? How many people have that problem? I mean, really, like how many people have this problem at home? Like that you have backups of backups of backups, and now you have so much stuff, and now you're like, I have 500 identical files of the same thing. In our office, this is a project we have to do right now. We have to go through these SON files. We have thousands of them, thousands that are identical, all over the place. Which is the real one? I don't know. We have to go through them each one by hand. So this is where you use the MD5 hash algorithm to figure out which one is identical. And here's the deal. And people always do this. This is what happened in the lab too. They found identical files. So we made this huge chart of the files. I'm like, just delete them. delete it. Delete the other ones. Don't be afraid to delete old ones and old versions. Another one is scan your records as text and not as pictures. I did that when we first got a scanner in the early 90s, and then when I got married to, and my wife was like, we're going to scan everything. We're going to scan all of our bills, scan all this stuff. Great, so we have it all scanned now, and it's in this thing called receipts.jpegs, and they're all named with that. So where the hell is the receipt? I don't know. You have to look through every single one, right? How many people have to do that? Have done that before, okay? And it's because we didn't include any metadata with it. We didn't even try to scan it to text at first. We didn't include any metadata. We didn't even name the file. We just threw it all in a. We had at one point we had a whole file cabinet. It was like this big, and we had this big scanner at work that they bought. It was like a $10,000 scanner at my wife's work, and she was like, "This is awesome." So she took this whole thing. I mean, literally, it's like take this whole thing of paper, just chunk it in there. It's like scan, 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 scan. So now we have gigs and gigs and gigs and gigs of pictures of bills from 2005 that we don't need, right? So the other thing is prioritize your data by the time to die. Data does have a death date. And the more you can get your data off of the, my data is so precious, everything is, that's the wrong way to do it. Because this is the reason why we got into this situation to begin with, is because we decided that every single keystroke we did in picture was the absolute most important thing to back up. All right, but really, anything that goes on like tax records, like 10 years, that's statute of limitations that can't come back. Just throw it away. Okay, receipts, try to there might be okay, for store receipts after 30 days, you're okay. But then if it's something like a tax thing, then stick it with the tax folder, right? So you need to put metadata with that. And then photos, that's up to y'all, depending on, well, is this because I've got actually so much photos now, and they're so big, and when I take a picture, and then 20 of them go in one click, right? And the iPhone does that, and it pisses me off. So you have 20 pictures of the same frame. And so when you back up your iPhone, then it backs the whole thing up. But really, I pull out the really good photos and put that in the, that should go to the next of kin. Everything else just goes in the backup, but I'm not really too concerned about it spot, right? That doesn't go in my offsite backup. So if there's a fire or something, I'm not really worried. All right, so case study. This is the Veterans Affairs Office. This is mostly a paper thing, but it's the same problem. So the article is that the people for the veterans were complaining that it was taking them years to get to their case. And they said, well, it's not our fault. It's really because we can't find your file. And so what it was is this is the 6th floor of some building. All the case files are on top of things. And so really they have a humongous L2 problem. Because there's no metadata, they don't know where the files are. They don't know where it is there. It is there, it's saved. I just don't know where it is. Whenever we come across it again, whenever we're finding things, we'll open your case. And sometimes that took months or it takes years. Okay? They also have a really big L1 problem where people thought because, well, if the place catches on fire, they have got no backup, plus of all this paper together. Also, they put so much weight on the floor was buckling and the floor was coming apart because of the weight. And then rot, this paper can rot. Also, they have a physical access problem because they've actually, to get enough space, they have to push the other file cabinets up against the other file cabinets so that you can't access half of the file cabinets at a time. And they say, well, next month we're going to move this out so we can get to those files. So we can't get to your file right now because it's physically blocked. Okay, so they have the 1, 2, 3 problem. So here's the other problem from the girl in the cube next to me, Lauren Hutchinson, who's a PhD candidate here. So her dissertation is about these marsh species and marsh species studies. So what she has to do is go through old publications, and she needs the data from all these publications to do a new study. So the problem is they didn't publish their data. And all these studies are from the 70s and 60s. So all you get is that. This is it. a graph that was hand-drawn. So her dissertation involves her mincing pixels to try to figure out where the mean is